Okay, so now we start with the forward biasing and reverse biasing. I think I explained yesterday in the previous lecture the forward biasing of the diode, right? I think forward biasing, if just I'm revising this, the forward biasing, right? What is the forward biasing, Sanjay? If this is the p-type semiconductor n side, and therefore when the positive terminal is connected to the p side, this is called the forward biasing. Are you getting or not? In this case, if you draw the current versus potential difference for the germanium, 0.3 volt, it is the cutoff potential. For silicon, this is 0.7. In some book it is written as 0.6 also, but it is fine. So in the forward biasing, you tell me, this is the majority, this is the diffusion current. What type of current is this? Diffusion. Plus, due to the majority charge carrier. Do you understand this thing or not? In this case, if you consider this is the forward biasing, the depletion width reduced, and if this is the p side, this is the n side, these are the hole are start diffusing from this side, and the electron are starting diffusing from this side. So the current is due to the electron plus hole movement both. Are you getting or not? And these are the majority charge carrier, and this is called the forward biasing, right? In the reverse biasing, I am explaining this again. Reverse biasing, yes. In the reverse biasing, what happened? You tell, Sanjay. If we see, this is the initial depletion width. This is the p side, n side. This is minus minus. These are the uncovered ion. Are you getting or not? This is open junction, unbiased PN junction. When this unbiased PN junction is connected in such a way that the positive terminal of the battery is connected to the N type, so the holes are starting supplied, right, from this side, and the electrons are starting supplied from this side, right? Therefore, they stick with this, right, and the depletion width is increased. They stick with the uncovered negative ion, right, and the depletion width is increased. Do you understand or not? The depletion width is increased, and the very high electric field is produced inside the material. Are you getting or not? No, and very small current start flowing. This is called the reverse saturation current, due to the minority charge carrier. I explained in the previous lecture little bit that when electron hole pair is produced between this depletion region, this is depletion region, right? When the electron and hole pair is produced, right, suppose this is the hole and this is the electron. Are you getting or not? So because of this high electric field, this electron, suppose this is the electron and this is the hole is produced, so this electron start moving in this way and the holes start moving in this way. Are you getting or not? Here in p-type, the holes are the majority charge carrier, so and the electrons are minority charge carrier. So you may consider when the hole come out from the depletion region to this p-type, it combine with the electron, and this electron is minority charge carrier in the p side, and these electrons are being supplied by this side. In the same way, this is the electron and it combined with the hole, which are the minority charge carrier in n side, and therefore these small hole number of holes are supplied by this side. So this process is called the drift, and the current due to drift of the electron hole pair present in the depletion region is called the drift current, right? Drift current start flowing. The current is what? Drift current, and it is very small. This is what? Drift current, right? This is drift current due to minority charge carrier, minority charge carrier. Do you understand this or not? For the germanium and for the silicon, right, you will see, if you consider the current in the diode and the voltage, this drift current does not change. It does not depends upon the magnitude of this EMF of the battery. If you are increasing the EMF, it does not change. For the germanium, it is of the nanoampere of the order, and for silicon, this is of the order of microampere, right? Copy this what you want. Listen one thing, this current flows in this direction, right? If you consider this the diode, right, and you connected the battery in this way, so the current, very small current, very small current, very small, how much it is, the minority charge carrier are very present in the very less numbers, so in the nanometer and the microampere, right, the current flows start flowing in this case, and this is called the reverse saturation current. Reverse biasing, this is called, IS is what, say reverse saturation current, right? Reverse saturation current, independent of voltage applied, voltage applied, whatever the voltage you applied, right, it does not change. Are you getting or not? Okay, although also listen one more thing, if this is the reverse saturation current, it does not change. Sometime it is represented in some book by IS, sometime it is represented by I naught. The thing is same. It does not depends upon the voltage applied over here, but it depends upon temperature. It depends upon temperature, temperature T. And for every rise of 10 degrees centigrade, this becomes double for every rise of 10 degrees centigrade, rise in temperature. So the current is what? Current as a function of temperature T is given as I naught, right? I naught, the current is what? Say I naught 2 की power T minus T1 upon 10. Are you getting or not? This is the reverse saturation current. Reverse saturation current, right? Reverse saturation current due to minority charge carrier. For example, listen one thing. How? Okay, copy this first. Please make it correct. This is the nanoampere current produced. This is the reverse saturation current. Nanoampere is the magnitude for the silicon, and for the microampere, reverse saturation current is for germanium. Do you understand? Please make it just a small mistake, right? Okay, listen one thing. If you increase the temperature by 10 degrees centigrade and the reverse saturation current become double. For example, if the I naught is the temperature on the 100 degrees centigrade, right, at T is equal to, this is T1 is equal to, at T2 is equal to 110 degrees centigrade. What is the value of the reverse saturation current? Can you tell me? 100 degrees centigrade. Every rise of 10 degrees centigrade, the reverse saturation current become double. So I am explaining this. So I dash, this is the I dash is equal to I naught 2 की power T minus, right, T, you may write T2 minus T1 upon 10, right? You may write like this. So at T1, the reverse saturation is current T2, and what is the T2? It is 110 minus 100 divided by, yes, divided by 10. So I naught is equal to 2 into 2 की power 10 upon 10 is equal to 2 I naught. So the reverse saturation current become double. Do you understand this thing or not? For example, if the reverse saturation current for germanium, for germanium, right, at T1 is equal to at T1 is equal to 100 degrees centigrade is, right, this is 50 microampere. Find its value at T2 is equal to, 130 degrees centigrade. This is the question. So this is the question. The initial current is what? Say 50 microampere, right? And the current as a function of temperature T is given as I naught 2 raised to the power T minus T1 upon 10, right? So I naught is 50 microampere, 2 raised to the power T. T become what? Say 130. Yes, definitely. And it is 100 upon 10, right? 50. Yes, 2 into 10 ki power 3 it is, right? And this is 50 into 8 at 400 microampere, right? Microampere. Do you understand this thing or not, you tell? Also, listen, how to do that? Listen, T1 temperature is what? 100 degrees centigrade. And for this, the 50 microampere. Understood, Sanjay? Right. For every 10 degrees centigrade, if it is 100 degrees centigrade, it become double, right? Now again 110 degrees centigrade, 120, it become double, right? And for again 10 degree rise in the temperature, it become 400. Although this is the one method, but if they ask for 210, then it will be very tough. So then we can use this formula to find the reverse saturation current if the temperature is increased, right? Copy this. So now we are discussing in detail, right, the forward wise and the reverse wise characteristics. Listen one thing, if this is the current, the diode current, and it is this the voltage applied, right, like this. If you apply the voltage, if the forward biasing, suppose this is the silicon diode or it may be the germanium diode. For the germanium diode, right, this is the 0.3 volt, right, it is the cutoff potential or the knee voltage for the germanium diode. And this is for what? For the this is for the silicon diode, right? So you just leave this, only you consider journal for forward wise characteristics. This is forward wise, right? You tell. This is the knee voltage. For example, if you consider this the germanium, so this is the 0.3 volt, right? So what is the knee voltage? Knee voltage or the cutoff voltage or cutoff potential also called 0.3 for germanium, 0.7 for silicon. What does it mean? You tell, Sanjay. For the germanium it is 0.3. If you apply, suppose this is the germanium diode, right? If you apply the 0.2 voltage, what will be the diode current in this case? You tell. If this is the germanium diode, you apply the 0.2 voltage. Yes, 0. So to on this is diode is off in this case. To on this diode, the minimum potential is 0.3 volt required. So this is called the knee voltage. For the germanium, for silicon it is. Are you getting or not? But if the voltage is, listen one thing, the voltage is greater than, for this is the germanium, voltage is greater than 0.3 volt. So the current in the diode is this. Do you understand? Suppose this is the, so for the different voltage, the current in the diode will be the different, and it is the exponentially increasing function. So what is the diode current I am writing? The diode current for the forward biasing here, it is given by I naught. The I naught is same as the reverse saturation current. Suppose this is the I naught, 1 e raised to the power, right, EV upon k into t minus 1, right? What is E? Is the electronic charge, K is the Boltzmann's constant, T is the temperature, V is the potential applied. Are you getting or not? So listen one thing, as you are increasing the potential, the current in the diode is increasing exponentially. Do you understand this thing or not? You tell. Right, Sanjay? Right, listen one more thing. If this is the V1, this is the I1, you may assume. If this is the V2, the current is also increase. So if you change, this is the change in potential and this is the change in current. Is it clear or not? So V is equal to IR. So resistance is what? Resistance is, if you want to find the forward resistance, the in this case forward bias resistance, forward resistance, right, forward resistance, right. The forward resistance is change in potential divided by change in current, right, like this, change in potential divided by. So for small change in potential, listen one thing, the characteristics is like this. For small change in potential, the current change is very high. Do you understand? So forward resistance is very less because it is approximately 0.1 volt, zero point 0.2 volt, and the current is very high. The forward, listen, one important point which is left. The diode forward bias diode current in this case is in the milliampere, and while the reverse saturation current is either in the nanoampere and it is in the microampere. But this diode forward bias current, due to the majority charge carrier in the order of, is the order of milliampere. So suppose the 0.2 milliampere current, right, this is the 10 milliampere current, suppose this is the 100 milliampere current is over there, right. So the forward bias resistance, you may consider this the 1000, so the 0.2, right. So forward bias resistance is very small. Are you getting or not? It is in the ohm, very small. Do you understand this? What is the resistance? Resistance is the obstacle in the path of the current. If you increase a small voltage, the current is very large, exponentially increasing. The current D, if you ignore this one, the current is exponentially increasing with V. If this is the V potential and this is the diode current, so it is exponentially increasing. So for the forward bias characteristics, for the forward biasing of the diode, the resistance is very, very small. Are you getting or not? You may consider this is the change in the current is what? 100 milliamperes, 1000 milliamperes, suppose. This is 0.2 volt, you may understood like this. Do you understand or not? So listen one thing. Ideally diode, if we consider the ideal diode, the forward right resistance is approximately 0. What does it mean? If this is the diode and this is the resistance, and if it is forward bias, right? So for this ideal diode, this is equal to what? The 0 resistance is produced in the circuit. Do you understand this thing? Suppose this is the 10 volt and this is the 5 ohm, right? So what is the current in this case? In this case, this is the 5 ohm, this is the 10 volt. So I is equal to what? V upon R, 10 upon 5. So diode current in this case is 2 ampere. For the ideal diode, this diode act as a wire, simple wire. The resistance is approximately 0, very, very small resistance. Do you understand this thing, Sanjay? Copy this. So this is the forward biasing characteristics. The resistance is very small, right? This is the practical diode. The resistance may be 1 ohm, 2 ohm, 0.5 ohm. But for ideal diode, we will assume it acts as a wire and the resistance is 0, right? Listen one more thing. Now in the same graph, you may draw the reverse bias characteristics. The reverse bias characteristic due to the drift current, due to the minority charge carrier. Forward bias characteristics due to the diffusion current, and the majority charge carrier. Right. Listen one thing. If you are You after this you may write the reverse biasing, right? Reverse biasing, right? In that case, you how to make this is the diode, suppose, right? And you are applying the potential like this. This is the reverse biasing. So this is the P side, this is the N side, and this is the positive terminal. So the reverse saturation current flows only, right? I know. In microampere for for germanium, for silicon it is in nanoampere. This is also the one question, right? Nanoampere. But if you are increasing the potential, it does not change. If you increase the potential, does not change. Increase the potential, does not change. Increase the potential, does not change. But after some time, when the potential is sufficient high, right, and at that potential the diode is damaged, or the breakdown of the diode is occur, and the very high current start flowing in it. Are you getting or not? For the silicon diode, this voltage is the breakdown voltage is approximately 30 volt, right? This is called the breakdown, right? If voltage is sufficient high, if the reverse bias voltage, is sufficient high, so that the breakdown occurs of the diode. Are you getting or not? Breakdown occur of the diode. The reverse saturation current is, right, very high current start flowing in it. If the very high current start flowing in it, due to temperature rise, right, due to a very high current start flowing in it, because of this, when the current is very high, the heat is produced and diode is damaged. Do you understand or not? And this is called the breakdown of silicon diode. The breakdown of the silicon diode occurs at 35 volt, while for the germanium, if you consider the germanium, this breakdown voltage occur at 25 volt for germanium. Do you understand? And for the silicon, it is reverse saturation current in nanometer. For germanium, the reverse saturation current in microampere, and its breakdown voltage is 25 volt. Are you getting or not? Copy this. So if we consider the resistance, right, if we consider the resistance in the reverse bias, yes, you will see, listen one thing, if you consider the resistance from here, right, you may see the characteristics like this, right? If you see, the voltage is very high, but the current does not change, very small. The resistance, reverse bias resistance, is equal to what? Delta V upon delta I, and it is very high. Are you getting or not? I am not giving the magnitude, just the voltage. Suppose this is the V1 and suppose the V2. So voltage is very high, but the current change in current is very small. Do you understand or not? So it is approximately, right, it may be approximately very high resistance in mega ohm, right, in mega ohm, the resistance in the reverse bias. Ideally, if this is the diode and it is connected to the reverse bias, suppose this is the resistance, the voltage, the ideally the resistance is infinite like this. So it act as a open circuit, no current flows in it. Ideally, ideal diode, the reverse wise, the diode act, ideal diode act as an open circuit, as an open circuit, while for the forward wise it act as a wire, the closed circuit, right? Copy this. Now there will be two types of question given in the exercise. First, for the ideal diode and for the practical diode, right? For example, if this is the question, suppose this is the silicon diode and its barrier potential is suppose 0.7 volt is given. It may be given 0.6 voltage or it may be given some other thing, right? Suppose this is the 10 volt. Are you getting or not? And this is the 5 kilo ohm. Are you getting? Like this. So what is the current? Find the current in this case. Find current in this case. So you tell me, if this is the barrier potential, if this is the diode and its barrier potential is given, it is practical diode. What does it mean? It offers, how much potential is offer? Say 0.7. So the potential will be dropped equal to the barrier potential offered by this silicon diode. So this is the 0.7 volt. It will act in the backward direction to this, right? And this is the 10 volt and this is the resistance. Are you getting or not, Sanjay? This is the 5 kilo ohm. So then what will be the current? So current will be equal to, what is the total voltage in the circuit then? No, 10 minus 0.7, because it is the barrier potential offered by this silicon diode. So 10 minus 0.7 is the total voltage, 10 minus 0.7, and what is the current? What is the resistance? Say 5 kilo ohm. Is it clear or not? So this is 9.3 upon 5 into 10 to the power minus 3. So the current is 5 एकम 5, 5 8 40, 5 36, 8.6 into 10 to the power 3 ampere, which is equal to 1.86 milliampere is the current flowing in this circuit. Sanjay, you are getting this thing or not? So this is the practical diode. Practical diode. Understood or not? Copy this. So in this question, although for the silicon and germanium it is 0.7 and 0.3, but especially in this question they have given the barrier potential. This is the diode, this is the resistance, and this is the EMF of the battery, 4.5 volt. So first of all, this diode is forward wise or reverse wise? Say forward wise, because positive terminal is connected to P and N, and the resistance is what? Say 100 ohm, and the barrier potential of this diode is given in the question, say 0.5 volt. Sanjay, is it clear or not? You tell. So what is the current in this circuit? V upon R, 4.5 minus 0.5 upon 100, it is 4 upon 100, right? So how much it is? You tell me. This is 1000 into 10 to the power minus 3 upon 40 milliampere is the current in this case. Copy this. So some other questions are there. For example, in this question there is a diode, the resistance, the battery, right? The resistance 10 ohm, this is the 5, this is the 30 ohm, the battery is 5 volt, and the current is given in the question is 0.1 ampere, right? They are asking the resistance, although the ideal diode they offer the zero resistance, but in practical diode they offer the some resistance, right? So if the resistance is R, then I is equal to what? V upon R. What is the total voltage in the loop? It is 5 volt. If I assume this the resistance R, then this is the 30 ohm resistance, and this is 10 ohm resistance. The current is 0.1, right, is equal to 5 upon R plus 40. It is multiplied by, and plus 4 is equal to 5. 0.1 R is equal to 5 minus 4 is equal to 1. This point R is equal to 1 upon 0.1, 10 ohm. So the resistance is of 10 ohm, right? Copy this. So this is the another question. In this question, there is a battery, there is a resistance, there is a resistance, the diode and the resistance, right, like this. This is 20 volt, this is 10 ohm, this is 10 ohm, 10 ohm, and this is the diode. Nothing is given for this diode, right? So I will assume this diode as an ideal diode, right? What is the value of the current? So if listen, one more thing, is it reverse bias or forward bias? You tell. It is positive terminal connected to this reverse bias, so therefore this act as an open circuit. So if it is open circuit, then the current flows like this. Are you getting or not? So this resistance is useless. So what is the total resistance in the circuit? You tell. Yes, the voltage is 20, 10 plus 20. So what is the current in the circuit? Say 1 ampere. Copy this. So can you read the next question? Very nice. So in this case, the two diodes are given, connected back to back like this, right, in parallel, and this is the battery and this is the resistance of the 1 kilo ohm, right here. You can apply. This is the 0.7 volt, its barrier potential. It means to on this diode, minimum potential is required 0.7 volt, and this is 0.3 volt. It is positive terminal, mean it is positive, it is positive, it is positive. You tell me. Yes, Sanjay. This current is asked. You tell me, it is forward wise or reverse wise? So it forward wise, and its barrier potential is given. So therefore, it offer the barrier potential of 0.7 volt like this. While it is, if it is reverse bias, it will offer the very high infinite resistance, and this is the resistance and this is the battery. And what is the EMF of the battery? This is the 2.7 volt. And what is the resistance? This is 1 kilo ohm. Are you getting or not? So what is the current then? You tell. Current is total voltage divided by total resistance. What is the V is equal to IR? The current is V upon R. The potential is 2.7 minus 0.7 upon the resistance is 1 kilo ohm. 2 upon 10 ki power 3 is equal to 2 into 10 ki power minus 3 ampere. 2 milliampere is the current, right? Copy this. So this is the one circuit, this is the battery, and this is the diode, right? This is the resistance, and this is the again a battery, right? This is the zero potential, and here is also the zero potential, right? Zero potential, zero potential. This is the 1 volt, this is 3 volt, this is the 200 ohm, and this is the diode. Are you getting or not? So how to listen one thing? If the diode is ideal, right? If diode is ideal, you can check this circuit whether it is connected in diode is connected in forward wise or reverse wise. If you assume this is 0, what is this potential? Say minus 1 volt. If it is 0, it is what? Say minus 3 volt. Are you getting or not? So you tell me, if this is diode, it is minus 1 suppose, it is minus 3 suppose. So which is higher potential? You tell. Minus 1, right? And this is the 200 ohm is also there, minus 3. So if it is ideal diode, so it is forward wise, it acts as a wire. This is the resistance. minus 3 volt, minus 1 volt, and this is the 200 volt. So what is the current in this case? V1 minus V2 upon R. Minus 1, minus 1, minus 3 is divided by 200. It is equal to what? Ampere. 0.01 ampere. Are you getting or not? Copy this.